So today we'll be speaking about the Sawhorse conformation. Apologies, I didn't start recording immediately. So please, if you have any questions, ask me after you watch this recording. But the Sawhorse, we are looking at a molecule through one of its carbon-carbon bonds. As an example, I'm doing ethane, okay? And I said that if you have ethane, okay, you're gonna have a carbon-carbon bond, then all the hydrogens will be at a 120 degrees. Now it's 120 degrees because when we look through ethane, okay, and we'll look facing opposite ethane, the angle will look as if it's 120, as if it is gonna be trigonal planar. We know it's not trigonal planar, okay, but when we look at it from the opposite direction, that's what it looks like. And in fact, the carbon-carbon bond can rotate, and now these are gonna be in a different arrangement. And when you look from the front, you will be looking and you will be seeing all 6 hydrogens. So the hydrogens can either hide behind each other, or they can be opposite. They can be in between each other, okay? So they can either be behind like this, or it could be the case that there's nothing in front of it, and the hydrogen is in fact between the 2 opposite hydrogens. Now, in fact, this can result in a number of different conformations, okay? This can result in a number of different conformations, okay? Now, what you've got here is a bit of a summary. So what I want to do first is I want to actually show you these structures, okay, from a different angle. And these are called the Newman projections, okay? So this was the Sawhorse, okay? Sawhorse, not seahorse, because that's the only thing I'm thinking of in my, between me and myself at the moment. Seahorse, I love seahorses, okay? But this is the Sawhorse conformation. Then there's also the Newman conformation. And the Newman conformation is actually looking at it directly perpendicular. So now, okay, you're gonna see 3 bonds. Let's draw that as your carbon. And from behind, you're gonna see another 3 bonds. So in this case, they are all hydrogens. But of course, it could be the case that they are not. So we will be doing this both when they are all hydrogens right now, like right now, or when you have 1 methyl, you can have 2 methyls, you can have a bromomethyl. So we'll take a look. And these can be either they are in between, or else they are perfectly behind. Okay, so when they are behind, like the moon behind the sun, or the sun behind the moon, it would be an eclipse, because they are eclipsing each other, they are hiding each other. When they are in between, there are two probable conformations where they are either staggered or gauche. Now, gauche and staggered, they do not mean the same, but for this particular example, there is no major difference, okay? When we use other examples, then we'll see. Now, the Sawhorse then is going to be a situation where we will only be using it so that we can draw these Newman projections, these Newman conformations, okay? And we can call them projections as well. Okay? And these Newman projections are going to be something very important, because all of the reactions from now on, we have to start thinking about the Newman projections. When we're doing mechanisms now, it's not going to be simply drawing a 3D structure, but it would be ideal, it would be best to draw these Newman projections. Now, we've drawn Newman projections for ethane. What happens if we have butane? And I'm going to analyze the C2-C3 bond. So I'm going to analyze this bond here, the C2-C3 bond. So now, if I draw my sawhorse, there's going to be a difference to what or where the methyl groups are. The methyl groups can be in the same direction, but this bond can rotate. And if it's rotating, then I can end up with the methyl group being opposite. Okay? So the methyl group is exactly opposite. And you can imagine that energy-wise, these conformations, these projections, would therefore have different energies. Now, the best way to do this is to actually discuss what we've got here. Okay? It's to actually discuss what we've got here. And here, okay, and here we can start thinking about them. We can start thinking about them from the perspective of you drawing these structures. It does not matter whether you first draw the Newman projection, you first draw the bond line template or the normal formula, the normal molecular formula, or else you draw the sawhorse projections. I would normally recommend starting with the sawhorse projections. Okay? I think it's easier. But every student is different, so find the method that works best for you. I'm going to make this emphasis. Find the method that works best for you. Okay? Now, so once you draw the sawhorse conformation, then you can start to try and have a look at what you've got. Okay? At what you've got. And for me, these two, for example, they are exactly identical. These two as well. But he's giving you different ways you might have been able to draw these bonds. And we're going to take a look because they would be different if you have three groups, for example. But I hope you can understand. Up is this group here, down is this group, right and left would be the hydrogens, whether they're coming in or going out. Okay? And again, by now, you should have gotten comfortable with building these structures, and it would be possibly very ideal to build these structures as well. Again, for the exams, for your annual for your final exam. I'm not entirely sure if you will be here at university or not. Currently, it seems that you might not be at university. Exams might still be online. Therefore, if they are going to be online, just make sure that you will be able to continue working on these thereafter, okay? And you can practice at home with the structures. If you're going to be here at university, I will give you permission to bring your materials with you, to bring your building blocks with you. Now, energy-wise, these become very important. And now, this is what you would need to start to think about. How will the energy change? So if they are completely eclipsed, okay? So if they are directly behind each other, and here it's calling it periplanar, then we'll review what periplanar would mean, okay? That's gonna be the highest possible energy. You cannot go higher energy than having two groups, two bulky groups, or the two bulkiest groups behind each other, okay? Then once you rotate, I think it's 60 degrees. Let's see, 0, 60, 1, 2, 0, 1, 8, 0, yes, 60 degrees. It's written at the bottom, it's me. Once you rotate 60 degrees, you are going to enter a gauche form. So gauche form is the lower energy form, where they are not perfectly opposite each other. They are not perfectly staggered, okay? And in fact, syn-periplanar would be where they are on the same plane, and anti-periplanar would be when they are completely opposite, okay? And this is gonna be important because in some reactions, we will require either syn-periplanar or anti-periplanar. And when we get to it, we will define these reactions once more, okay? When we get to it, we will define these reactions once more, okay? Now, if I rotate another 60 degrees, I'm gonna end up in another eclipsed form. But this time around, instead of having two methyl groups touching each other pretty much, I have a methyl group being hindered by a proton. Protons are smaller, therefore we will have less repulsion, there will be less electronic hindrance. And this, in fact, is lower. This, in fact, is lower in energy than when you have something which is syn-periplanar, or you have a complete eclipse of the two bulkiest groups. If I have it at 60 degrees, now I go into the anti-periplanar, where they are completely opposite. Okay? When they are completely opposite. And at this point, you have the lowest possible energy. Then there's going to be another eclipsed mode. And in fact, these two eclipsed structures are the same. That's why earlier on I told you that these two are identical and these two are identical, because we only have two different conformations. We have only two different substituents, a methyl and the hydrogen. Another, at 100 degrees, we'll end up in another gauche form, which is the same as the first gauche form, but now we're gonna see what happens when you have three different groups, okay? And then we're going to have the starting product, and these two are the same, okay? So you have done a full 360 degrees, okay? And you end up starting and ending in the same position. What I would like you to do is to try and draw, okay, the conformations or the energy diagram for this molecule here. And in around 5 minutes time, we will discuss it and we will see what is actually happening. So I'm gonna give you 5 minutes or till past where you can actually go on and discuss. I'm gonna try and see if I can prepare some breakout rooms where you can discuss this between yourselves. Let's wait for the others until they leave their breakout rooms. It seems that N is keeping her group overtime, with all of group 3 staying there till now. So, welcome back, all of you. For room 3, if anyone was being kept hostage by Mrs. Grima, please do advise. Because
they were not. We were discussing. We used the entire time to discuss. Thank you very much. What did you say, Gabe?
Oh, isn't she? Because she told us to stay, but it was very polite.
Yes, I said we can stay, and nobody left. So I technically politely kept them hostage.
That's fine, we forgive you. Or they forgive you. So, now, the way I would do this would be to start, but first of all, by ending up drawing the Newman projection. So whether you drew this as first item or not, okay, it does not really matter. And because I'm lazy, I will be copy and pasting that all throughout the place. So we have CH3, Br, hydrogen, and then I would do the eclipsed, and this would be my highest energy. Okay, so this is my highest energy point, and I know that if I'm gonna plot the graph, I'm gonna start somewhere here. Okay. Then we can rotate a little bit. Okay, rotate by 60 degrees. And if I rotate by 60 degrees, I will get to B. I will make sure that CH3, Br, and hydrogen remain the same. So in fact, I could have copied all that. Okay, but now we have a CH3, Br, and hydrogen. And these are gonna be, of course, lower in energy, but they're not gonna be the lowest possible point. Okay, why? Because now we're going to have a situation where your structure, okay, where your structure is going to be lower in energy when you rotate by another 120 degrees, okay? But you might not know that. In fact, normally, you might want to sketch this first. After that, we're gonna draw when we shift by another 60 degrees. C, and they're gonna be CH3, Br, CH3. And at this point, hydrogen. At this point, the CH3 and the Br, they are going to be exactly behind each other, and this will have some electronic effects. Therefore, in fact, C would be a bit higher. But it's not gonna be as high as A. And the reason it's gonna be as high as A is because A, you have a bromine behind another bromine. Two big, juicy atoms. You can then rotate another 60 degrees. Okay. And this will be D. And now we're gonna have the fully antiperiplanar. And this is gonna be the lowest energy because the bulky groups are completely opposite each other. There is still going to be some repulsion between the methyls and the bromines, but there's gonna be more space between the methyl and the bromines than would have been between bromine and bromine, or methyl, methyl, bromine, bromine. So this would be the lowest end of the spectrum. Okay. Then we will end up repeating the same process where you'll have another C, another B, and we end up onto an A. The reason is because this molecule was symmetrical, okay? I could have been harder and harsher and gave you an unsymmetrical structure, but I opted not to, okay? So please do realize that if I were to shift by another 60 degrees, I would end up having something similar to C, okay? So let's see it. Hydrogen, bromine, and methyl. Gabriel.
Yeah?
After and keeping you hostage, did you at least do it correctly?
I mean, we didn't really have a space where we could write, but this is pretty much what we did for the most part. At least like around C or D, because then we discussed the symmetry part.
Symmetry. I gave you a symmetrical one nonetheless because I thought it was going to be a bit easier for you guys. Okay. Now let's actually move these. It was a bit easier for you guys, but don't worry. Okay.
What we were gonna do was one of us was gonna share screen, and then we were gonna annotate on it. Emma, you disabled the participants share screen, so it went a bit slower than.
Sorry.
It's okay.
For next time, apologies.
Yeah, no, I'm just informing you.
Yes. I'll see how to do it for next time. Okay, so you can actually discuss and you can use share screens. I will be using this method because now you have some knowledge and you can actually start working with each other. You know each other as well, and hopefully that should be relatively nice. If someone can't stand and doesn't want to be in the same group as N, please do advise, because I have the option of removing people from groups.
I know you're joking, but like, I wouldn't be surprised if you got a message.
She was really helpful. I
wouldn't be surprised if someone messaged you and told you they don't want to be in a group with me.
I'm using it as an example, okay? Now, if that were to happen, I will not tell you, and don't worry. Now,
no, of course, don't snitch on people, but like, I wouldn't be surprised.
Now, listen. After that, I would like to speak a little bit about the conformations for cyclohexane. So, what do you know about cyclohexane? What are the conformations you are comfortable about when speaking about cyclohexane?
The chair and the boat.
The chair and the boat. Now, the chair and the boat are two possible conformations, and we're going to be speaking, or at least introducing the topic today. And then after, in fact, I'm only going to discuss these conformations, okay, and how they interconvert. I will show you a little bit of a GIF, and then we'll discuss a little bit further after your holidays. I mean the exams, but you would have lectures, so it's holidays, and you have the carnival holidays in between. I'm pretty sure no one will go and celebrate and enjoy them.
When are the carnival holidays?
Second week of February, I believe.
I think we have exams then.
Yeah, I'm still pretty sure some people will go and get drunk. That's what we used to do back in my day. I turned out
we have exams and then we go straight into lectures, so that's why I wanted to ask. I was hoping we'd have like more than a weekend.
I don't think you do, because at university you don't get the carnival holidays, neither you will get the November holidays. So I would be very surprised if you were. You're not at SEC anymore, and
All right.
privileged people. Now, I will be speaking about the chair and board conformation. Now, in reality, you have 120 degrees. 120 degrees is quite a nice angle, but if you're gonna have 120 degrees there, then it means that the other bonds are gonna be much less than 109 degrees. That is acceptable for an sp3 hybridized carbon, and therefore you would want to try and avoid them. So what you do is you have the boat and the chair conformation. Okay, so this is the boat here, and these are the two chair conformations, and you can see that the hydrogens can actually end up being on opposite sides. Now, I'm not too interested in asking you to know how to draw the change in conformation from one side of the chair to the other. So the chair can either be like that, okay, or it can be on the opposite side. You can start from top and go to the bottom, okay? So that chair these two would actually have slightly different properties because they would be complete mirror images. Now, I'm not too interested in getting you to learn how to change them from one to the other, okay? But there is something very important. This is the axial and the axial hydrogens. So I think it was this one. Yes. Okay, axial and equatorial hydrogens. So what I want you to realize is how to draw these. Now I'm gonna send you this page because I have found it very useful when both preparing the lesson, okay? But it has some very interesting GIFs that you can take a look at, and you can rotate these accordingly. And apart from that, you can then even highlight, okay, certain hydrogens, okay? For example, where was it? Equatorial, axial, okay? And you can revise it through here. So let's actually go through this page relatively quickly. Then go home and read it. You can read it, in fact, after the exam. It's not a problem, okay? You can read this after the exams, so prior to the next lesson. And then we'll just close off this chapter with regards to cycloalkanes, okay? Because this is not going to be true just for cyclohexane, but we'll also be doing cyclopentane, cyclobutane, and cyclopropane, and we're going to be discussing what these are, okay? Now, so this is the planar. Planar is quite unstable, okay? And this is the most stable structure, which is a chair conformation. Trying to get it to be not gonna manage to rotate it. Okay, and this is the chair conformation. So the chair conformation, you've got the axial and equatorial hydrogens. The axial hydrogens are perpendicular to the ring, okay? And the equatorial are around the plane of the ring. So axial, let's highlight all of them, okay? So they are the ones in red, okay? Though they are perpendicular. They are gonna be 90 degrees above. Okay, you can see how to draw them here. Okay, those are the axial hydrogens. And you have the equatorial, which is gonna be in the plane, okay? Around the plane of the ring. Now, something to note here, if you need to draw if you need to draw the equatorial positions, so the axial, they're easy. They're up or down, okay? The axial positions are easy. They're up or down. But you have parallel lines. So those are parallel, okay? Parallel and parallel. So keep this in mind and that should help you. Okay, keep this in mind and that should help you. Because they are parallel and because they are parallel, therefore you would be able to get them and you would be able to draw them accordingly. Also something important, okay, let's try and find it here so I don't have to show my skills. When you draw them, okay, let's try and get them in a nice, neat position. When you draw them, axial and equatorial, they might not be the ones, so let's then rotate this, okay? So the hydrogen that we're seeing here on the first structure, which is the planar one, going out, the first one would be axial, second one would be equatorial, axial, equatorial, axial, equatorial, okay? So there is, I forgot the word at the moment, one axial, one equatorial.
Alternate.
Okay, alternate. Yes, that's the word. Thank you, and you're a lifesaver. So you don't need to hate Anne, okay? Just thank her for all the work she does, and you can bitch about her with me without her knowing.
Yeah, sure, that works. Sure.
Now, so alternates, okay? So one would be equatorial, one would be axial. And that should help you when you want to draw something going from the planar, because remember, you will normally be starting to draw them as planar going into the ring. And that's what we're going to be doing once we come back, once we meet again. Okay, now this is actually very important because it helps you see what reactions are going to happen. Okay, and whilst it's quite nice to actually try things out, okay, and draw them accordingly, okay, you might want to actually do these and see how they work at home by using sticks and balls, okay? When I told you those are going to be one of the most important that you're going to have, I meant it. Now, someone sent me a point group symmetry. These are mostly more important, so I can show it to you. These are mostly more important for inorganic, okay? Not sure if you've done them or not yet. If I can find the one for cyclohexane, I will find it, I will show it to you. But I don't know the point group symmetry for cyclohexane by heart. Okay. Now, and in fact, here you can see them a bit clearer. So it's gonna be perpendicular to the ring, or on the plane of the ring. These would also have their own energy diagrams, which we will be drawing in our next lesson, okay? For today, we will be stopping here. Let's stop the recording.